Hey, this is Robert Quimby, and I'm going to tell you about the Bootstrap method for evaluating the uncertainty in your analysis. The name for this technique is derived from the old expression, pulling yourself up by your bootstraps, which in modern times means to do something without help from others. The connection here is that when you report a measurement, you need to indicate the range of outcomes that others might find when they repeat your experiment. But you need to figure out this range by yourself just with the data you have. Actually, this expression was originally meant to evoke an impossible task, but we will see here that with a large enough sample of data, you can actually predict the range of experimental outcomes that others will find quite well with just you and your data. So I'm going to start this tutorial by telling you just what the Bootstrap method is, and then we're going to actually go and do some examples to really get a better sense for how you can use it. We'll be looking at the uncertainty that we get from the Bootstrap method and compare that to standard uncertainty propagation techniques. But we can actually apply Bootstrap techniques in cases where we can't do uncertainty propagations. It just is impossible to do. So in the process, we'll show some of the things you might want to use bootstrapping to do. And we're also going to hear about a related technique at the end called jackknifing. So the first thing you got to do if you're interested in applying the Bootstrap method is you need to start off with a sample of data that's sizable. So you go out and collect some number of observations. Really should be at least about 30 samples, but really to make this work well, it's best if you have hundreds or thousands or even millions of observations in your data sample. So you gather all those, and then you apply whatever statistic you want to this sample. And by that I mean you should apply whatever analysis you're going to your data to get whatever results you want. So perhaps you're measuring the brightness of a star and you just want to know how bright that is. So you take a series of measurements and maybe you're just going to take a simple average of those, and that's going to be your analysis process. So your statistic in that case is just simply your average. But you can do this for anything. It could be a median, or you could be fitting a line to some data, and the statistic you care about in that sense might just be the slope of the line. So here's where bootstrapping comes in. What you do next is you take that original sample you have, that sample A, and you're going to randomly draw values from A with replacement. And what that means is you think about having a hat with all your values in it, and you pull out one of the values from the hat, and you look at it, you record what you have, and then you put it back in the hat. That's the replacement part. You shuffle up everything, and then you draw another value from that hat. And you keep doing this. So at the end of the day, you're going to have a new sample that's going to have the same number of elements as your original sample, but in this new sample, some of the values might be repeated, and some of the values that were in A might actually be missing from your new sample B. After you've gathered your new sample B, what you do is you apply that same statistic. So again, if you're calculating the average of a bunch of magnitudes, you just calculate the average of that new sample B. Or if you're fitting a line to some data to determine the slope, you just use the data you have in B and fit that line. You then repeat this whole process of resampling many times. And many isn't well defined here, but it should be a large number typically. So you might want to do this 10,000 times, for example. Depends on how much data you have and how long this whole process takes. Maybe you don't have time to do it 10,000 times. Then once you get all of those M results, you can take them all together and you can look at the distribution of those values to figure out what the uncertainty is in your original measurement. So before we get to the example, I just want to remind you that what you're saying when you produce a measurement and you have some uncertainty in there is you're telling other people who might repeat your same experiment the range of values that they could expect if they exactly repeat your experiment. So if you make some measurement, you don't just say, I measured magnitude of that star and it's 5. No, you say it's 5 plus or minus, and you give some range so that when they go out and they make their own measurement of the brightness of that star, by the randomness of nature, they might get a slightly different answer. And they have to figure out if the star has changed in brightness or if this is just that randomness playing out. So to do that, you give them this confidence interval where you say, I'm confident that if you repeat this experiment, you're going to get a value between here and here. So when we do bootstrapping, what we're actually trying to do is replicate that whole process. We want to have thousands and thousands of different measurements of the same thing so that we can look at that distribution and know that when someone else, the 1,001st person, goes and makes a new observation, we're going to say here's the probability of getting different results so that they know when they get a result how likely that is given what we've already established. So the key behind bootstrapping is that instead of going out to the universe and just taking new data and analyzing that, what we're going to do is we're going to use the data we already have. And we're going to use that as a stand-in for what the universe supplies. So we're going to assume we have a large enough sample so that the randomness of nature is contained within our sample. And so that when we randomly draw values from our sample, we'll get results that are similar to if we just randomly drew new data from the universe. So you can think of this as having a parent population versus having a sample population. And if your sample is large enough, it should reflect the parent. And so by randomly sampling from the sample, it should give you results that are comparable from randomly sampling from the parent. So the upshot here is that we can, instead of repeating this whole experiment, which is very costly, we can just take the data we've already collected, and if it's large enough, we can randomly resample from that to get an idea for the range of results that other people are likely to get by repeating the experiment. Now keep in mind the accuracy of our results are going to depend on how large our sample is and how well it actually reflects what's available in nature. And there's always some random chance in there, so our results could be a little bit biased. So now we're going to move to a concrete example of this process. I have a little function that I've created here, and what this is going to do is this is going to simulate the data that we might gather in some experiment. So there may be a star somewhere in the universe that has an actual magnitude of 18.5 mag. We can conduct observations of this with our telescope, and we can determine what its magnitude is in our data. Of course, due to the randomness of measurements, we're not going to get exactly 18.5 every time. We may have some uncertainty in our measurements of, say, 0.2 magnitudes. And maybe we'll collect 50 different observations, and then we'll take all these together and use those as our sample to figure out the brightness of the star. So all this function does is it just basically simulates some data. It just creates some random magnitudes drawn from a distribution that's centered on 18.5 with some uncertainty given by our measurement uncertainty here, and returns that sample. So now what we can do is use that function to gather our simulated data, and then we can perform some analysis on it. So the analysis that we want to do here is we just want to know the average. So I'll write a very simple function here that returns the average. I could just use numpy average, but I'm going to write it out explicitly. So I'm going to do numpy sum of our sample magnitudes. And I'm going to go ahead and divide this by the number of elements in our samples. That's just the sample size. And then I can call this function, passing it our data, and I'll get our result. And we'll see what our result is. This will be the average magnitude of that star according to our random sample here is 18.5. So again, this is close to what we know the true magnitude is because we created this fake star here. It should be 18.5 exactly. But there's some randomness in our measurement, and we'll see that here. So again, the question becomes, what if somebody else runs the same experiment and they get a result? How can they compare that to our result? If they get 18.53 magnitude, does that mean the star got a little bit fainter, or does that just reflect the randomness of nature? So what we need to do is we need to report, when we report this magnitude, we don't just give it by itself, we give an uncertainty with it. And the object of that uncertainty is to tell other astronomers the range of values that they're likely to encounter given our result. So what we really want to know is what is the distribution of values that other astronomers are going to get if they repeat this experiment. So given our framework here, we can just simulate this. We can say, hey, we can go and ask maybe 10,000 of our closest astronomer buddies and tell them to do the exact same experiment. So they're going to collect some data the same way. It has to be the exact same way we do it. So they're going to get their star data with the same function here. Get their star observations. And then they're going to do the same analysis on that. And for each one of these astronomers, we're going to perform this little experiment, and we're going to collect all the results in one list. And then what we can do is we can make a plot of this just to see what that distribution of values looks like. So if I run this, we can see that this is the range of values that they're likely to get. So they're most likely to get a value around here, 18.5, but there's a chance that they might get 18.55 or 18.6, maybe even there's a small chance they'll get out there. But what we're going to quote, what we should quote, is the value that we get and then some 68% confidence region. So we can directly calculate this. Since we had our 10,000 astronomer buddies go and do this, we can actually take the mean of all the results, and that's the expectation value. And then we can take the standard deviation of the results, and we can look at these, and that'll tell future astronomers when the 10,001st astronomer tries this experiment that they're most likely to measure a value of 18.500, and then there's an uncertainty in this. So our 68% confidence region is plus or minus 0.028 magnitudes. So then they'll know if they repeat this experiment and they get 18.57, well, that's pretty unlikely. But of course, we may not want to always call on our 10,000 closest astronomy buddies to repeat our experiments because they got things to do themselves. So what we need is a way to estimate what this range of outcomes is going to be from our experiment without actually doing 10,000 repetitions of the experiment. So we've talked about one way to do this, and that's actually through using uncertainty propagation. So we know that the result we have is just based on this simple algorithm here. So we can apply uncertainty propagation to that. And if you remember that, we just take this function that we have that defines our result, and we take partial derivatives of it with respect to each one of our variables, and in this case, each one of our magnitudes. We multiply that by the uncertainty in each one of those. We square it, we sum them all up, and we take the square root. And that, if all the measurements are independent, that is going to give us an estimate of what the uncertainty in our measurement is. So we can do this. We'll take the numpy square root of the numpy sum of, and then we need those uncertainties for each one of our measurements, which is just my sample emag. And then we square these values and then divide by the sample size squared. Okay, that should be my sample, and I have this parenthesis in the wrong place. Sorry about that. Yes, so we take the sum of the squares, we divide it by the sample size squared, and we take the square root of all that. And then we can calculate that the uncertainty from uncertainty propagation, just from our data alone, would be 0.028. So that's a demonstration of why we do uncertainty propagation, because it's giving us this result without having to repeat that experiment. But as we'll see later, we can't always do uncertainty propagation in some analysis techniques. So we need another independent way to do this. And this method relies on having accurate uncertainties for each one of our observations, which we may not always have. So we might want an independent way to assess the uncertainty in our measurement. So that's where bootstrapping comes in. The way bootstrapping works, as we talked about earlier, is that we take our sample, our one sample now, and we're going to apply some analysis to it. That's going to be our function here. So we're going to apply that to resamplings of our sample data over and over and over, and then record the distribution of values we get. So we can do this in Python pretty straightforward using NumPy. There is a random choice function, which is very handy because you can give it a sample, and it will randomly draw from that sample to give you a new sample. And we'll do this with replacements, and you can specify the size of the output array you want. We just want that to be the same as our input size. Once you've created that sample, you can call whatever function you want on it. This is your analysis function, so maybe you're calculating the mean or the median or the slope of some line. And we'll record that, and then we'll return all the distribution of all those different numbers. So now we can apply this to our sample here that we've gathered. So we'll just gather some sample based on this procedure here and get star observations. Our function that we're going to use is the analysis we've been using before. Same function we defined earlier. We're going to do, say, 10,000 of these iterations. And then we're going to do our bootstrap distribution from that sample. And then we'll just plot the results that we previously calculated when our 10,000 closest friends did this experiment. And we're going to compare that to what we get from bootstrapping here. So let's see what that looks like. So there we have it. So the blue distribution here, that's the distribution we saw before. The red line here, this is our one value from our experiment. We did the experiment and this is what we got here. And then when we bootstrap the sample we got this distribution here in kind of this peach color. So this whole distribution here is what we would predict. If we didn't have our 10,000 friends do this experiment, we would say, okay, we think the best value is here based on our results, and this is the range of values we might get. And you can see, you can actually rerun this cell multiple times because it's resampling every time. And you can see that every time you do this experiment, you can get a different result. And that result sometimes is going to be reflective of the true answer, and sometimes it might be a little bit off. But the important thing to note is that the width of the distribution we get from bootstrapping is actually very similar, very close to the width of the distribution that we would actually get by repeating this experiment 10,000 times. So that's telling us that we can use this bootstrap distribution to actually estimate the uncertainty in our measurement. This is the mathematical formalism for how we do that. What we do is we take each one of the outcomes from our bootstrapping, each one of the results we get, each one of those 10,000 results, subtract off the known result. So the known result is the one that we get from our actual sample, our original sample. We apply our analysis to it, and we get some value. We subtract that off from each one of those 10,000 iterations, square it, sum it up, and calculate the average. So m here is 10,000 in our example. Take the average of that, get the square roots, and that is going to give us an estimate of what the uncertainty is in our result. So we can put this into Python here for our particular example here. So we're going to take the numpy square roots of 1 divided by m times the numpy sum of our distribution minus our result of our analysis. So we'll take our function and apply our sample to that. We'll square this here. And then we'll see our bootstrap uncertainty is estimated to be 0.0295. So this is very close to that value we previously got. So the true value, remember, is 0.028. This is what we would have gotten if we had asked our 10,000 closest friends. But without even bothering them, we can get a very, very similar uncertainty. And of course, if we repeat this experiment many times, we'll get slightly different numbers here. So keep that in mind. This is somewhat dependent on the randomness of nature. So there's a little bit of uncertainty here. It could be slightly systematically different depending on the systematics of our sample. So since this is not exactly right, you probably, in this case, would want to just simply use the uncertainty propagation formula. You'll get the exact answer, and you can move on there. But what if we don't trust the uncertainties in our observations? So each one of those observations, we have some uncertainty that we put in. We said that when we recorded data that we're going to have an uncertainty of 0.2 in each one of our observations. But how do we know this? Well, we have to estimate this somehow, and it's possible that we could estimate this incorrectly. So maybe we thought we had an uncertainty of 0.2, but actually the real uncertainty was larger. So what would happen in this case? Well, we can work that out by using this veramag option that I put in this little function here. What that'll do is it'll increase the scatter in our distribution of values by some amount. So we can use this to simulate the fact that maybe our error bars are underestimated. So I'm going to put in an uncertainty of 0.5. This is going to be on top of what we think we have. There's actually going to be a much larger uncertainty, a scatter. You can think of this as either our uncertainties being underestimated, or maybe we're looking at a variable star and actually is moving around. So every time you look at it, you're getting slightly different values. So let's see what the effect of this is on our whole process. I'm going to rerun this cell here. I'm going to rerun our sample here. Let's see what our observations get. Yeah, we still get the same thing that time. We could run it again and get slightly different numbers. That was just kind of a chance result. We'll go back again, ask 10,000 of our friends what they get. We'll look at the distribution that they get, and this is going to change a little bit. So now there's actually a slightly wider distribution here, because when our friends go out and do this, each one of them, they're again thinking they have an uncertainty of 0.2 magnitudes in each one of their observations, but it's actually larger, or perhaps the star is variable. So this is broadening this distribution from before. So when we look at what the standard deviation of those observations is, it was 0.82 before, but now it's 0.076. And if we just go and naively apply our uncertainty formula, again, our uncertainty formula relies on us having accurate measurement uncertainties in each one of our measurements. And if these are not accurate, then we'll get a result which is different from what our friends are going to derive. So this could lead to a problem. Our friends could go out and they could make a measurement and it's going to be different than ours by more than we would expect given our calculated uncertainty. But that's only because we have a problem with our measurement uncertainties here. So let's see how bootstrapping applies here. So we have that same bootstrap function that we calculated before. We're going to get a new sample here, apply the same analysis we did before. So everything we did before, except we made a change here to this function to add that extra error. And we can see that even with that extra uncertainty there, we see that the width of this distribution that we get from bootstrapping is still pretty well matched to what the others actually observed. We can apply this formula here, and when we see what our new uncertainty is, this is still close to the scattering results from our 10,000 closest friends, even though we didn't say anything about the uncertainties in our measurement in this whole process. We're actually just using the data themselves to figure out what the actual uncertainty is. So this shows one of the strengths of bootstrapping. Even if you have measurement uncertainties and you don't trust them, you can use bootstrapping and that'll tell you an estimate for the uncertainty. And then you can look at that and say, how does that compare to what I would have expected from uncertainty propagation? And I can tell you, maybe you have a problem in the uncertainties for your data. Another advantage of the bootstrapping process is that you can actually apply it even in cases where you can't do uncertainty propagation. So let's do a different set of analysis. Instead of finding the average brightness of the star, let's find the median brightness. So here's a function here. This is our new analysis function, analysis 2. We're going to pass it a sample, and it's going to return the median. Now, I've written out some lines of code here to actually calculate the median instead of just using NumPy median, because I want to remind you what this process is. And you'll notice that this is a discrete process. This is not a continuous process, because we're using this integer division here to get an index. So we can't take a derivative of this process. There's no way we can do uncertainty propagation on it. However, we can do bootstrapping on it, just as before. So we're going to use our new function, we're going to apply it to our data, we're going to get some results. We find that the median brightness of our star in our 50 samples is 14.46. We can go to our friends, we can ask them to do this new analysis here. So take the data they had before and take the median instead of the mean, calculate that. And we'll get some distribution of values. It has now an uncertainty, so the distribution of their values has a width, a sigma of 0.093. You'll notice that this is actually a little bit larger than we found for the mean. This is generally going to be true because it turns out that a mean is actually a more precise measurement of a sample than a median. So the uncertainty is actually going to be a little bit larger for a median. So again, we can't use uncertainty propagation, so all we can use is bootstrapping, but this is exactly what we did before. You just have your function that you want to apply to your data, you have your sample of data, you apply that function to it, and then you calculate the uncertainty by looking at the distribution of values you get. And there you go. We get a number which again is very close to what would have been calculated if we had done this 10,000 times separately. But we're just using our own data to get this value. Let me tell you about a related process now called Jackknife, which is also useful in evaluating the uncertainty in your results. What we do in the Jackknife method is you take the sample of data that you have, those n data points, and you actually just throw out one data point and then measure your results using the n-1 points that are left. And then you throw out a different data point and you measure a result, and a different data point and measure a result. You keep doing that until you've thrown out every data point in turn, you look at the distribution of results that you got, and then you can use this to evaluate the uncertainty in your result. And this is particularly useful if there's bias from one of those measurements. Maybe you have one measurement which is a little bit off. It can help you determine if that's the case. So here's a function that we can actually use to calculate this Jackknife distribution. All we do is we take our sample and we're going to apply some function to each subsample of the data in turn. The subsamples that we're going to use are just going to be the whole sample except for one value. So it's going to be in this for loop here. We're just going to do it everywhere that the index is not equal to some particular value. And then we apply this just as before. So we'll have our Jackknife distribution. We'll give it the sample that we want, the function we will apply to it. And we can look at what this Jackknife distribution looks like. So here's the outcomes from our trials. Again, in this case, you just get n-1 values. You don't get the 10,000 values that you could get with bootstrapping. But you can still look at this distribution and you can calculate what the uncertainty is. The way you do this is slightly different than the way you calculate the uncertainty in the Bootstrap. And that's because these samples are very correlated. So we have this extra factor here of sample size minus 1 divided by the sample size, which is going to help correct for that correlation. So when we run this, we can see that we're getting a Jackknife uncertainty for our sample of 0.08 magnitudes. And if you remember, the uncertainty from uncertainty propagation was just 0.028 magnitudes. So if we compare that with the Jackknife value here, we can get some idea that maybe the uncertainties are underestimated. So lastly, I just wanted to point out that all these methods, the bootstrapping and Jackknife, are actually built into AstroPy stats. So you can just use these functions. You don't have to use the bootstrap dist or the Jackknife dist functions that were defined in this tutorial. You can already find versions of these in AstroPy. The functions they have are slightly differently defined. For example, in the AstroPy stats bootstrap, the order of the parameters is a little bit different. So just as an example, if you wanted to use the AstroPy bootstrap function, you would give it your sample, you tell it how many iterations you want to do, and then you define what function you want to apply to analyze your data using the bootfunc keyword. Or again, analysis was whatever process you want to apply to the data at each of these 10,000 steps. But otherwise, it's very much similar. The jackknifing is done in two different functions in the stats package. And so this is a little bit different than what we did, but at the end of the day, it's the same basic process. So I hope this gives you some idea of what bootstrapping and Jackknife are and why they might be useful, and enjoy.